Hey, let's talk about distances briefly. How we know how far away stars are, at least stars that are fairly close to the sun. How it's done is the method of something that should sound familiar called parallax. What we do is we look at a star from two different points of view. And then we look and see how it jumps, right? The example we used before was you put your finger in front of your face, you close one eye and open up the other eye, and it looks like your finger jumps. And what you do is the further away you move your finger away from your nose, the smaller the jump. So the amount of jump has to do with the distance. All right, so that's exactly what we do. Except instead of two different eyes, we substitute for that the position of the Earth going around the sun. So here I have a diagram, like maybe a star is right here. Here's the sun. And then none of this is to scale, right? This is just a cartoon. And so here's the Earth in, I don't know, like January as it goes around the sun. And then when it is 6 months later, I don't know, something like July, maybe the Earth is over here on the other side. So when we look at the star from January, you follow that sight line and it looks like maybe the star is at that point. And then when we look at the star in July, it looks like the star has jumped a little bit. So what we do is, in theory, is we look at the star and we look at the amount of jump. And the amount that the star jumped, there's a certain little angle that it's jumped through, and we measure that angle, and that's called theta. So it's jumped that amount of angle. It turns out that once we know the angle, and if we know the amount of what's called the baseline, so that's the distance of the Earth from one point of the orbit to the other point in the orbit, if we know those two things, then we got it. Then we can calculate d. I'll show you roughly how it's done, just to give you an idea of how it's done. Look, this amount of angle, imagine that this were completed around an entire circle, right? We know that there's 360 degrees in a circle. So here's what I'm going to do. I'm going to set up a proportion. So we know that this amount of angle compared to the total amount of angle around the whole circle, this is equal to this amount of distance compared to the entire circle. If you imagine, this is not exactly a circle, but you get the idea, all the way around the star, right? So that amount of angle compared to the whole circle is like that distance compared to the total distance all the way around. Okay, what we do is we say that that distance is about 2 AU, right? It looks like it's going to be pretty close. So 2 AU is sort of the straight line distance, but that's not going to be too far removed from this amount of curved distance. So we say that this is 2 AU compared to the total distance all the way around. And you have to go back and remember, what is the distance all the way around a circle, the circumference of a circle? Well, it's 2 pi times the radius, right? And the radius would just be this distance d. So it would be 2 pi times d. Neat. Okay, so that's how we actually figure this out. So the amount of angle compared to the total angle is like the amount of distance that the Earth goes compared to the total distance. That's how we do it. Okay, so let's work with this a little bit. Let's just take what turns out to be an easy case. Let's say that this angle, and I'm picking this angle on purpose. I'll tell you why in just a minute. Let's say that the angle was 2 degrees. The star jumped 2 degrees. How much is that? If you put one of your fingers almost out at arm length, that would be about 2 degrees on the night sky. So let's say a star jumped that much. Okay, then that means 2 divided by 360 is 2 AU over 2 pi times. The thing we're interested in, remember, is D. I want to know how far away that star is. So, well, from algebra, I can cross out those 2's. There's one on the top, one on the bottom, so they divide out. 2 divided by 360, that's like 1 over 180 is just 1 AU over pi times D. Okay, so let me go ahead and solve for D. I'm just going to do a tiny bit of algebra just to show you how this works out. So D, if I bring D up to the other side, D is going to be 180 divided by pi AU. Well, you can plug that into your calculator. Pi is something like 3.141592.6, right? Keep on going. So this is going to be like, if you do this, I already did it. It turns out to be about 57.3 AU. And remember what an AU is? That's the distance to the sun. So this says if a star jumps by 2 degrees, then I know, just from geometry, I know that it's 57 times further away than the sun. Very cool. Now, no star jumps 2 degrees. Otherwise, that would have been seen in the ancient times. And remember, the deal is that in ancient times, they never saw parallax shift. So the parallax shift is much smaller than that, which means stars are much further away than that. This is just for instance, it's just an example. But this is how we figure this kind of thing out. It's just a direct measurement. Notice all we have to do, the only thing we have to measure is the jump on the sky from 2 different times 6 months apart. And then we can just calculate the distance. So it's a pretty simple measurement. If we can measure the jump, then we got it. We can calculate the distance in one step. The way we actually do it, let me show you what we actually do. This is a way to set it up in terms of things that you're a little more familiar with. What we actually do is this. Because it's defined more exactly this way, we actually call the parallax angle is half of the total shift. The reason why is because, look, this makes sort of a right triangle. And it turns out that there is a trig function. If you've had trig, you might know the trig function tangent. It's a button on your calculator. Anyway, the way it goes is, here's the distance. That's also the distance to the star from the sun. And so the tangent of this angle, if you've never seen this before, it's not a big deal. So the tangent of the angle is 1 AU over D. So D is 1 divided by tangent of the angle in AU. That's what we really do. We use trig functions to calculate this, but it doesn't matter. We get about the same answer. Either way, I'm just saying, I just include this. If you've had trig before, there you go. This is how we actually do it. And this is why I think in the book it mentions that the parallax angle is half of the total shift, and that seems like, why would you do that? This is why we do it. It's just easier to calculate this way. This is called, by the way, it's not just stars. This is called the surveyor's method because you can do it to measure all sorts of really cool things, like the height of a building or the height of a mountain. If there's something that you want to know, what's the height of something? Maybe it's a tall tree or whatever. If you want to know the height of the tall tree, but you can't climb up the tree with meter sticks, right, to figure out how tall it is, here's called the surveyor's method. Here's what you do, is just walk away from it some distance x, and then you just sight up to the top of the tree some angle, and then you can calculate it. Because if you walk a certain distance x, then you can calculate the x, or you can calculate the h, because tangent theta is h over x. So the height is just x tangent theta. This is not important. I'm just letting you know that this is something, it's not something astrophysicists invented. This is something that was around for a long time. It's called the surveyor's method, and surveyors use it all the time. And this is how you can calculate how tall things are without actually having to go up and measure them. I think in the book they talk about getting the distance across a river. You can use this. It's also called triangulation, right? You get a distance across the river. You don't actually have to cross the river. You can just measure along the river, and then you get an angle, and then you got it. So this is just a common way of measuring distance. We just applied it to stars because, look, this diagram is the same as that diagram. It's the same geometry. So this is how we find distances to stars. Okay, for real stars, let me say it this way, not for the closest star. Remember what that means. The closest star is going to have the biggest jump. It's going to be the most easily observed. For the closest star, theta is about, how big of a jump is this? It's about 1, those little tiny marks means 1, arc second. Or 1 arc second. Here's how it works. 1 degree gets chopped up into 60 minutes. That's one little mark. That's a way to measure tiny little angles. 1 minute of arc is about the same, just in everyday language, it's about the same as a period at the end of a sentence of a book, if you hold it at arm's length. 1 minute is about the limit for human eyes. That's about the finest detail that we can see. But you can chop each minute up into 60 seconds so that there are 3,600 arc seconds in 1 degree. So it's a teeny, tiny little angle. Way too fine for human eyes to see, but we can measure it with telescopes, no problem. So 1 arc second, so the jump for the nearest star is only 1/3600th of a degree. Very, very tiny jump. And when you plug this in to what we had done before, 1 arc second jump means that the star is about 200,000 AU away. That's the distance of the nearest star. Is it's 200,000 times further than the sun. That's a lot. If you were to do it to scale, if the sun were a basketball, you could ask, okay, where is the nearest basketball in that scale? So if you wanted to make a scale diagram or make a scale model of the nearby stars around the sun, if the sun is a basketball, that's not a very good scale because the nearest basketball to the sun would be pretty much in Hawaii, about 4,000 miles away. Stars are incredibly separated. If you scale it down even more, if the sun were a golf ball, the nearest other golf ball would be in another state, pretty much in Dallas or Kansas City. So stars are separated in the sun's neighborhood. The stars are separated about like 1 golf ball per state. So they are extremely far away and extremely spread out. So what's the likelihood of 2 stars just sort of running into each other? Very, 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 very small. Okay, so this is sort of a special distance. If a star jumps by 1 arc second, we know its distance is about 200,000 AUs. And if that's the nearest star, notice we're getting into a problem again. It's sort of like, we used the example before of measuring the distance to a city like Denver is 1 billion millimeters away. Could be true, but millimeters isn't really the right unit to use, is it? It's just too tiny. So when we went to the solar system, we got AUs. That's a little bit better unit to use. But when we talk about stars, now stars are so far away we have to now scale up again and use a different unit. So what we do is we just call this, because it turns out to be convenient, 200,000 AUs is 1 parsec. The abbreviation for parsec, you'll see in the book, is PC. Parsec stands for parallax second. It's the distance you get if the parallax jump is 1 arcsecond. So it turns out to be sort of an important thing. And that sets the scale for distances between stars. Stars are separated by some number of parsecs. The closest star to the sun is about 1 parsec away. In terms of light years, something you see in the book, it's about 3.26 light years. So light, traveling at as fast as light goes, 300,000 kilometers a second, would take 3¼ years to cover 1 parsec. It's very, 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 very far. Okay, so this is how we measure distances to stars. It's a teeny tiny little jump, but it's measurable. In the 1990s, we managed to map the closest about 500,000 stars to the sun, believe it or not. We got good parallax measurements for those stars, and so we were able to start constructing a detailed map of all the stars within about, I forget, it was about 100 or 200 parsecs of the sun. Just 2 years ago, data came in from the latest mission called Gaia 2, and Gaia measured distances of the nearest about 2 billion stars. We have good parallax information for about 2 billion stars, which covers a good chunk of our galaxy. Our stars are arranged, you might know, in what's called a galaxy, called the Milky Way galaxy, and there are about 200 billion stars in the Milky Way, which is a lot, but we've managed to map about 1% of our local region of the Milky Way. Very cool. So we have really, really good distances to many, many stars, 2 billion stars or so, that are closest to the sun. And next time, we'll show you what we can do with this information. The distance is critical, because remember how it goes. If you know the distance to something and how bright it looks, now what I can do is calculate how much energy it's emitting. And that's going to be really valuable for us in the next unit, is to figure out how much energy are these stars actually putting out. Because when you just look at it, you don't know. A star looks dim, but you don't know if that's because it's really dim or maybe it's just really far away, right? There's an interplay of those two things. But once we have the distance to the star, then we got it locked down. Then we can calculate, based on how bright it looks, we can calculate its wattage, right? How much energy it's actually emitting. So that's where we're going next time.